Thanks to everybody on the Zoom conference tonight, the live stream on our YouTube channel. If you like it, give it a thumbs up and subscribe if you're not subscribed. We have, again, over 1,000 subscribers now on YouTube, so that's great. And everybody that came over from Meetup too. And introducing our speaker tonight, Dr. Teresa Nieves Chinchilla. She is a research astrophysicist in the Heliophysics Science Division of the Goddard Space Flight Center. And she's also a NASA project scientist for the Solar Orbiter Collaboration and an adjunct professor at the Catholic University of America. She has over 17 years of experience in the study of electromagnetic fields, space plasmas, and energetic particles as they relate to the understanding of the properties of large-scale structures of the solar wind. Now, prior to joining GSFC's Heliophysics Science Division back in 2009, it's easy for me to say, through the NASA postdoctoral program, she worked from 2006 to 2009 studying the temperature and electron density properties in coronal mass ejections using data from the WIND spacecraft. So Dr. Nieves Chinchilla has over 70 publications in professional journals that include the Solar Physics Journal, Space Weather Journal, Astrophysical Journal, and the IEEE Transactions on Plasma Science. So won't you please welcome us tonight from, well, she earned her PhD in theoretical physics in Madrid, Spain. She's not there now. Please welcome Dr. Teresa Nieves Chinchilla.
Oops.
Ah, there you go. Yeah, I still can't hear you though.
Sock puppets now.
We're going to be doing flashcards.
We heard you before.
Well,
No.
I don't know. Can you hear us, Doc? Oh, something's happening.
I think she's going to try again.
Yeah, I think she's either reconnecting or...
Yeah, that's okay.
she's muted also, right?
No.
Well, not muted through Zoom.
Okay.
All right, let's see.
Can you hear me now?
Yes.
Yes.
Oh, sorry. So weird. Thank you very much for the introduction. I was amazed for the tornado that you saw. It was amazing. Nice. Who did this picture of who took the tornado, the solar tornado?
Yeah, the guy that took the tornado is not a member. It was up on spaceweather.com is where, that's what I showed. That's what I was posting. And his name is Apollo Lasky, and he took that March 17th from Naperville. So on St. Patrick's Day, he was in Naperville, Illinois, and he took that. So he's not one of our members. I wish he was, but man, that's an amazing shot regardless. It doesn't matter.
Now I lost you,
crazy.
Dan. I can hear you.
Okay.
But is my fault?
I think that's on your end. We can hear you.
Can you hear me all?
Yes.
I don't hear you, but anyway,
Okay.
I'm gonna go ahead because I don't know why I don't hear you. Anyway, so make a sign if something happened.
Okay.
Okay.
It looked like you had earbuds earlier. I don't know if
Okay. So thank you very much for the introduction, and thank you very much for it's an honor to be with this team, with this group tonight, and introduce Solar Orbiter. I know probably you have heard about this mission. It's the latest mission for NASA, Solar Heliospheric mission for NASA, and also for the European Space Agency. Solar Orbiter is a joint mission from these two agencies. It is led by the European Space Agency with a strong contribution from NASA, and then also NASA participated with operation, with instruments, and also during the development of the mission, NASA was the responsible for the launch from Cape Canaveral. I'm here all today to talk about Solar Orbiter, but also in representation of this whole meeting, the whole group and team, which is you will see is very large. So during this presentation, I will motivate the mission, the Solar Orbiter, why Solar Orbiter exists. And also I will go a little bit more in the technical details aspects about the instruments, the orbit, the lifetime of this mission. And then I will bring some of the discoveries of this mission that it's been in the space for 3 years, just 3 years. So we live, let me go here, and here is, okay. We live in the extended atmosphere of one star. Oops, can you, okay. This is, so we live in the atmosphere of the sun. This atmosphere is formed by the solar wind. This is an outflow of magnetized plasma that it comes from the sun radially away in all directions. It goes in velocities in the range between 200 kilometers per second to 800 or even beyond the 1000 kilometers per second, and goes beyond the solar system and reach the boundaries of the heliosphere. Oh, no?
No, about 30 seconds ago, your slides disappeared.
No?
No.
Okay. Let me go back again. I don't know why. So let me go back, disconnect and reconnect again. Don't you mind?
Nope, that's fine. Okay.
Stand by?
Yeah.
Yes.
Meanwhile, Dan will sing us a song.
Oh my.
Dan will sing show tunes.
When the moon hits your eye like a big pizza pie, that's amore. Yeah. Well, I'm glad that Alex has good snipping skills.
Yep.
So
will be a
all
more
this,
complicated edit.
nobody's going to ever see any of this stuff. It's going to be just like butter. Smooth. Not enough O's and smooth.
Okay.
All right.
We can hear you.
Now you can hear me.
Can you hear us?
I'm gonna launch the presentation.
Can you hear us?
I can hear you.
Okay.
Let's see if now it works. Can you see the presentation?
Yes.
Okay, let's go then. Let's
Right.
go ahead. Did you hear the beginning, the first slide?
Yes.
Okay, so in the second slide, I was trying to just highlight that we live in the extended atmosphere of the sun. And then you can see here the solar wind that I was talking about, this magnetized plasma that is flowing from the sun away in all directions. Obviously, we are protected by the magnetosphere, and sometimes that just go through. But sometimes it goes through the magnetosphere, as in this animation you can see, is going through the magnetosphere, and all the energy of this plasma is coming to the earth, to the ground. And this is sometimes we don't, because we are living in the earth, we don't really mind what is going on outside. But when this magnetized plasma get into the magnetosphere, we start to care about what is happening out there. And now that we are also trying to explore the space, we are starting to realize that we really care what is going on in the space. So I know this group knows very well what is going on can you see the slides?
Yes.
Okay. What is going on with the sun, and I'm gonna go too much into this detail. Just to some facts, the sun is a young adult star. It was created almost 5 billion years ago, but it's gonna be around for another 5 billion years. And is located in the Milky Way, as you know, with 250 billion stars around. It's nothing special about our star. In fact, the period around the galaxy, the center of the galaxy, is all these 220 million years. So we are not gonna get or have any galactic year, right? Then the rotation in the star around its axis is the mean value of 27 days, and is 109 times larger in size than the Earth. In terms of mass, we estimate that is 2 with 30 zeros kilograms, and most of the mass is concentrated in the core. But we can say that the mass, the 90% of the mass of the solar system, of the heliosphere, it is concentrated in the sun. Based on the so I was talking about the energy that is released in this fusion process. So the energy that is released takes 200,000 years to reach the sun's surface. But once the photon reaches the surface, it takes just 8 minutes to get the Earth. So in general, how we understand the sun is very simple. It's just a dynamo. And we have poles and the magnetic fields. And we know that basically this is the physics around the sun. But actually, when we go and dig a little bit more into that, it seems that it's more complex than the dynamo that we thought it is the sun. And here is some details about this. So in general, I was saying that 27 days is the average period for one turn of the sun, but actually it's not. And it changed with the latitude. In the equator, the observations of the plasma in the sun's surface say that the average of the rotation is about 25 days. And however, in the poles is 35 days. So the plasma moves in different velocities in the pole and the equator. So if we think that this is magnetized plasma, so the plasma is frozen into the magnetic field lines, we have currents moving in different directions with the latitude. What happened? This occurs in the sun. So what happened is that it develops currents, electric currents, and Maxwell equations tell us when we have gradient in currents, we have also magnetic fields that are accumulated where the gradient is happening. So in this accumulation of the magnetic field, we start to observe these dark areas right here. And these are the sun poles. So when the sun starts to accumulate this magnetic field, we start to see the sun spots. And these sun spots, dark areas, usually come in pairs, because one is positive and negative. It's just accumulation of the magnetic field that is increasing with the solar cycle. We know that the solar cycle takes around 11 years, and then we see the accumulation of the sunspots in the sun surface. And what happens when the energy is increasing? Well, we know that as increase the energy, this energy needs to be released. And this is what we see also in this movie from SDO. Solar Dynamic Observatory is one of the satellites, NASA satellites, that is located at the Earth position and is going with the Earth, observing the sun surface all the time. So we see these explosions, big explosions of the magnetic field and plasma from the sun that are known as coronal mass ejections are coming from these active regions that are formed by the sun spots. So we have increase in the magnetic energy, and these are going toward the solar maximum that we know. And then eventually, when all this energy is released, the sun comes back to the solar minimum, and we don't observe then these accumulations of the magnetic field. We have been observing for centuries the sun's surface. We know lately more closely, right? But we know that the solar cycle lasts for around 11 years. What we don't know, and I put here this slide is not updated because we are already in the solar cycle 25, but is just to highlight the fact that we are counting sunspots and we are putting them in a plot, in a graphic like this, and we see the solar cycle 21, the 22, the 23, and the 24, but we don't really know why we have less sunspots in these solar cycles. What is happening in the sun? How this dynamo works differently in each of these solar cycles. This is one of the mysteries that is still in the field, and we don't have answer to this question. So we talk about these big explosions, and then we have solar observatories. We have here a map. This map is from 2013. We have observatories at Earth, and we have observatories around the sun. SOHO is one of the observatories located at Earth, and is observing the sun with different instruments. Here we have one of the instruments. This is called a coronagraph. Coronagraph is just an artificial eclipse that is covering the sun's surface and allow us to see the corona, the faint corona. And we see this big explosion that is very similar to the one we observe with SDO. But what is happening here is that this big explosion is coming also with energetic particles. These white dots are just saturation impacts of the energetic particles in the CCD camera that is saturating, and eventually it may damage the telescope. So in this other movie, we have the composition of two instruments on board of two different satellites. We have SDO, that, as I say, is located at Earth, and we have stereo. In this case, is stereo A, is one of these. Stereos are two twin spacecraft that are going in at the distance of Earth is 1 astronomical unit. They are going around the Earth. The sun, and now in these days they are back to the Earth, and they are very close to the Earth. In these days, in 2013, we have successive. It was a period of a lot of activity and many coronal mass ejections, and we were able to compose with SDO the stereo coronagraph and track from the sun surface the coronal mass ejections all the way in the heliosphere. Well, this is an animation just to understand how we see or how we understand these coronal mass ejections. These are big explosions with huge amount of mass and energy that is released from the sun and is moving radially in all directions, in any direction, eventually can reach and impact the Earth. As I say in the beginning, when it reaches the Earth, just because we have the magnetosphere, the superpower of the magnetosphere, and is protecting us, these events, these explosions just come through and pass without even, realize that something is happening in the space. But sometimes, because of the interaction, meet some physical properties or things. So the shield, this magnetosphere, it opens and allows the entrance of the radiation and energetic particles into the magnetospheric system. When it happens, a lot of, as I say, energetic particles and radiation reach the Earth's surface. In these occasions, we can have these beautiful aurora borealis that we have many beautiful pictures that I will show later in the presentation. But also this radiation can damage our technology in the atmosphere. So these are the coronal mass ejections, and these are sometimes very, as I say, very dangerous. This is the case of the extreme space weather events that we call, and I brought here 3 very popular and historical events, but we have many others very often. So the first case was the Carrington event. Carrington was an astronomer, as you are, and in 1859 he was observing a group of sunspots in the sun. This is a drawing from him. It was a huge amount of sunspots at the sun surface, and he observed also an explosion. So it was a very interesting communication among different astronomers and different locations. What happened is just one day after the observation of the explosion from this area, telegraph in the high latitude were completely damaged, and the communications through the telegraphs were shut down. So it happened 200 years ago. The technology in the society, it was not actually happening, right? And so it was just the telegraph. So 2 more events that in the last century, one in 1921 and the second one in 1989, I highlight here because the first one was 10 times stronger, and we have better reports of these events. It was 10 times stronger than the case of Quebec. In the case of Quebec, not just the communication in the high latitude, but also Quebec was without power for more than 8 hours, the days after the event. So as we dig into more of the events, we have damage in the satellites, we sometimes lose communications in the GPS. So we are starting now to understand the impact of the sun in our life, in our societies. And sometimes we think about the things happening in our technology, and we don't understand that it happened because of the sun until now that we come back and see the relationship between what happened in the sun and in the space, what is happening in our technology at Earth. So we have lost many satellites that we didn't know that it was because of the sun. So here just want to illustrate a little bit what is, the impact of the sun activity in our lives, from the ground, even below the sun, the sea level. We can have impact in the submarine cables or telluric currents in the pipelines. We have also events in the ground level with power in the power system. Obviously now the crew on commercial planes are more careful about the number of hours that they are flying, and depending also of the itineraries. So we are starting to understand the relationship between, for instance, the lightning with the sun activity. And obviously in the level of the ionosphere, we understand the ionospheric currents are affecting to the satellites. And sometimes we have dragging in the satellites, we have lost in the GPS sign from our satellites. And now that actually we are thinking about exploring the space, and I'm going to be talking too much about that Artemis program that I think is very interesting, but I don't have time to talk about this now. But now that we are thinking to go to the moon, not just to visit the moon, but also to stay there and to use the moon as the platform to go later to Mars. Now we have to think about how to protect our astronauts from this radiation, and we have to think also to protect our technology, because we want to take care of the astronauts in the journey to the moon and later to Mars. So in order to do this, we need to understand our sun, and we need to focus in the two questions that are in the top of these slides. How does the sun create and control the heliosphere, and why does the solar activity change with the time? So by answering this question, we can protect our technology at Earth, but also our, ambitious to explore the space. And this is the main motivation of Solar Orbiter. Solar Orbiter wants to contribute to answer this question, and to do so, there are 4 here questions that our community, the team of Solar Orbiter is committed to answer. The 4 questions are how and where the solar wind is created. And to do so, to answer that question, we need to track the sun activity and disentangle the space-time of the structures. And to do so, we need to track over the time these structures in the sun surface and explore the source of the solar wind. We need to understand the transients, these coronal mass ejections, large structures that are bringing variability in the heliosphere, how they evolve, how they change, how they drag energetic particles. And this is related with the 3rd question that is very important for us, for the space exploration, how these energetic particles are produced at the sun and how they are evolving, or maybe also how these transients are accelerating energetic particles from the sun. And then the 4th question, which is related with the dynamo. I have been talking about this variability, or the change in the rotation of the plasma at different latitudes in the sun. We never have been out there at the poles. We never have seen the poles, and we don't really know what is going on right there and how change the currents right there. So Solar Orbiter is gonna go there and observe the sun poles and bring, hopefully, some answers to the questions about the solar cycle. So Solar Orbiter, and this is just a summary of the mission. It was launched in February 10 in 2020, right before the pandemic. It was here in the East Coast. It was on the night of the 9th of February. It was a beautiful night that I saw some pictures later. So the mission is around 10 years mission. We want to answer all these questions in 10 years. It's very ambitious, but probably it's going to happen. And then the mission will have is having 3 phases. The cruise phase that already passed. During this phase, just the in situ instruments, and I will talk about the instrumentation on board, but just keep in mind that during the cruise phase, we have just the in situ instruments working all the time, and then the remote sensing instruments, the telescopes, were testing during this period. It was almost 2 years. And then in November 2020, we start here with the Earth Gravity Assistant Maneuver, kick off the nominal mission, which it will last for 5 more years, and then at the end of the mission, the extended mission, it will be 3 more years. During this period, we will be going closer and closer to the sun to get a distance of around 0.3 astronomical units, being 1 astronomical unit. You know that, but just for those that don't remember, astronomical unit is the distance between the sun and the Earth. And then we are going to get 0.28 astronomical units, and the periodicity of each orbit, around 22 orbits, are going to be around 6 months. So every 6 months we will be at this distance, or more or less at this distance. And one of the milestones of these missions will be to bring the first observations with telescopes of the sun poles, and with an inclination of the orbit of maximum 33 degrees. Also, another of the milestones will be that the reduced relative rotation that will allow us to track, as I say at the beginning, these structures and the source of the solar wind, and hopefully to bring some answers about the source of the solar wind. And here it is, the beautiful solar orbiter. This is the spacecraft, 3-axis stabilized satellite facing the sun and protected with this shield. The shield is a special technology that is isolating the instruments that requires quiet temperature and obviously more fresh temperature that the temperatures are 0.3 astronomical units, but also because we need observe the sun's surface, we have these small windows that allow the telescope to peek through the shield and observe the sun's surface. Because we are gonna, the distance to the sun is changing, the solar arrays change, are articulate to get the maximum energy from the sun, where the maximum distance, and be protected when it's very close to the sun. And the high gain antenna that is folding back and forth to communicate with Earth and to bring all these beautiful observations from the sun. And then in terms of the instruments on board, I talk about in situ instruments. In situ instruments are all these 4 instruments that are taking measurements of things happening around the satellite. Energetic particles, magnetic field, radio and plasma waves, and also plasma elements of the solar wind. So each of these instruments is leading by different countries. When I talk at the beginning that this is a joint mission between Solar Orbit, European Space Agency, and NASA, I'm talking about a big collaboration among many countries. And I can tell you there are 10 instruments on board Solar Orbiter, 4 in situ instruments. These are 4 countries leading each of these instruments, but within each of these teams, there are also many collaborations, international collaboration. This was one of the challenges of the Solar Orbiter because of the different cultures, different languages, but I can say now that it was a successful challenge and beautiful exercise for the international community. So coming back to the instruments, in terms of the remote sensing instrument, telescope, we have different wavelengths observing the sun surface, and then we have also different instrument observing also the corona and the heliosphere. We have the coronagraph, METIS, and the Solo High, which is one of the US instruments that is observing the heliosphere from the corona and beyond. And we will see some of the images from this instrument. So a little bit of history of Solar Orbiter. Solar Orbiter was thought decades ago, I will say from the 80s. So we have questioned in the community, in the heliophysics community for many years. And we knew, I say we because, but I was even, I was a child when these questions were brought into the community. These questions have been here for many years, and we knew that we had to do what we are doing with Solar Orbiter to bring technology closer to the sun and to the poles, but we didn't have the technology. So that's why the exercise during all these years, first of all, within the scientific community, formulating the questions, and then also the exercise with the engineers. As I say here, without engineers, science is just philosophy. The scientists we want things, but engineers put the reality on the table and say, hey, we can do this now. And it happened with Solar Orbiter, and it was in 2012 when ESA assigned Airbus Astrium by then to be the company building this satellite. And this is the satellite weeks before it was brought here to the US to be launched. And these are the teams. These are just a small portion of the huge team of Solar Orbiter, the European, and here with the rockets, with the Atlas V on the 9th of February 2020. This is the US project office with the project manager and the engineers, and here Solar Orbiter is within the head of the rocket. So the satellite was successfully launched in the night of the February 9th. And this was, as I say, a beautiful launch in the night. Like you can see this picture. I was very honored and grateful for being there with my family. It was an experience in life. And then COVID came. COVID came. I'm talking about February 9, 2020, commissioning activities. Commissioning activities is when the satellite, we turn on all the functioning devices and all the instruments later. And then it happened right after, and it had to happen right after the launch because it's when the satellite that was close to the Earth, and then we were able to have a fluent communication with the satellite. So usually this happens in the mission control center. In this case, it was in Germany. And then all the teams, you always travel to there and work with the ESA folks or into the turning on the instruments. But what happened is the pandemic didn't allow us to go there. So everything was happening in Zoom, and it was a challenge because even for those working at ESA in the Mission Control Center, they were restricted to go there. So I can tell you a lot of stories about this time, but this is just one of the PIs of one of the instruments working with the ESA members and working with his team. He's from UK and also US members here were working with him. From here, it was a challenge, but I can tell now that it works. In July 2020, we have our first live of the all instruments, and we claim mission success, at least for the first light of the of the instruments. And here I just want to highlight the lifetime of the satellite. Here is the distance to the sun, the solar latitude, and this is the timeline of the mission. So from 2020, in yellow is the cruise phase, in pink is what is a nominal mission and will go until the extended mission here later until 2030. So what happened is how we are going to get to the sun, how we are going to go above the ecliptic plane. Well, we are going to use the gravity assistance from Venus and from Earth. So during the cruise phase, we use the gravity assistant 1 and 2 to get closer to the sun, as you can see, and then with the gravity assistant from Earth, and it was the last time Solar Orbiter is close to Earth. So we start to be closer to the sun, reaching the distance of 0.3 astronomical units. And then it was the beginning of the nominal mission, and the nominal mission during the whole nominal mission, we are going to be at this distance, back and forth in each orbit to the distance. And then we just passed last year the gravity assistant 3, and then we start to elevate the inclination of the orbit of Solar Orbiter, and then in 2025 is when we are going to have the following gravity assistant, and then we will start to move, this inclination, higher in the orbits. So this is, and then it will be in the extended mission when we are going to be closer to the sun, but also with very high inclination of the orbit, and then we will bring these beautiful pictures of the sun poles. But during all these times, and this is one of the first results in 2020 in the nominal mission, in the beginning, in the first perihelion of the nominal mission. These are images from EUI, one of the telescopes in ultraviolet wavelength. We are observing the poles, not completely the poles, but in the limb of the poles. This is the Earth scale, the Earth size, and this is the higher resolution that we never have seen the sun. We can see these details of we were talking about the tornado, the flow of the plasma, these tiny explosions with movement of the plasma falling back and forth to the sun's surface. We see these small explosions. There are many details that I'm bringing the attention of the scientists. And talking about the details, one of the most, let's say, omnipresent observations in the sun, or surprise for the scientists, are called the campfires. It was very popular, the campfires, because it seems that campfires on the sun's surface were everywhere in the sun. We never have seen this tiny explosion in the sun. It was a big surprise, and that's why they called these events campfires. They are in the times, they are in between 10 and 200 seconds in the period, not the period, the duration of these events. They cover in the surface between 400 and 4,000 kilometers in the sun surface, and they never have been seen before. And as I say, and it was very interesting for the community. And then what the scientific community brought attention for one thing. There are another mystery, a big question in the community, and it's about the change in the temperature in the sun's surface, in the sun atmosphere. There is a layer in the sun atmosphere called the transition layer, where the temperature is higher than the sun's surface. This has been observed for many years, and it was a big discussion in the community how the sun atmosphere can be hotter than the sun's surface. And then now with this discovery or with these observations, the scientists are starting to think that these campfires are the main responsibles of the heating of the sun atmosphere. Actually, there are many right now studies ongoing in the community, doing computer simulations, trying to combine, and as I will show in the following slide, combining observation, taking measurements, putting together numbers, trying to see if actually these campfires or nanoflares or small explosions are summing up the enough energy to be able to heat the sun atmosphere to the temperatures that we are observing. And here, for instance, is the combined observations. So this is, again, the collaboration within the Solar Orbiter team. Two instruments observing the same area. We see here first the campfire, and now with phi, with the polarimetric, we are able to see also the magnetic field on board the solar, in the sun surface, and combining both, we are able to extract the amount of energy responsible to create these campfires, and then eventually to know how much energy can we add to all the campfires and see if they are the responsible of the heating of the sun atmosphere. So moving on to different observations, we have been observing one of the things of the challenge in the solar orbiter is combining, putting together different pieces of the puzzle in order to understand the whole picture of what's going on in the sun. And this is the case of the energetic particle event in March 21 in 2022. And it was combining the observations of the X-ray from STIX with UI, and we were able to see the wave, the shock wave, that are also the jet, the flowing of the energetic particles that eventually hit the spacecraft, and it was collected by the energetic particle instrument. And then we were able also to see how develop Langmuir waves also, and see how ionize the plasma in the solar wind, in the magnetic, in the solar wind. Also, another observation, very interesting, from Solar Orbiter, from one solar flare here. It was a multi-instrument observation of this. Here, again, combining, and you very well known that combining different wavelengths, we can see different physical processes associated with the same event. So with X-ray, we can see the process of the reconnection and the release of the energy within this process. And it was a very interesting event, analyzed also for the community to quantify the amount of energy that it was released in this big flare. And also, just for enjoying the eyes, combining with other instruments here, with a satellite, Solar Orbiter, combined with SOHO, and different instruments of SOHO, we were able to track structures all the way from the sun surface to the heliosphere. Here you can see a coronal mass ejection and a wavelength, shock wave moving away from the sun. And here also very interesting, I talk about in each orbit the telescope are observing around the perihelion, but also during every day the telescope are taking observations. And this is a movie from an astronomer, also Finlay, that is putting together and observing in the, in one solar cycle, in one orbit, how the sun evolved. With just one image every day. But this image, this is just for enjoying, for having fun and seeing the sun, how it changed in each orbit. But actually for the space weather community is very valuable information. For instance, this is how Solar Orbiter is helping to track the sun activity and to make predictions that are affecting to the Earth and the technology in the space. This is one event in March 2022. SOHO observed from Earth, observed with all the instruments these big, huge coronal mass ejections on 10th of March, and then it results that Solar Orbiter was in halfway between the Sun and Earth. At Earth we have SOHO and wind, and then we were able to track and see, here is the magnetic field, and we see this structure here in the magnetic field that later at Earth was also observed. These structures, these coronal mass ejections observed by in situ magnetometer, are the main responsible of the geomagnetic observation and geomagnetic activity. And in this case, we had this beautiful aurora borealis. But the thing is, we were able to make a more accurate prediction thanks to Solar Orbiter and eventually protect our technology. And just, I want to wrap up here. I'm sorry, I'm taking a little bit more time than I expected. Just to summarize that we are right now in the nominal mission. It's coming and very hot perihelion. Now in April 10th, we will get the 0.28 astronomical unit distance from Solar Orbiter. Coming exciting results, and Solar Orbiter, as I say, is all about collaboration. It's working with other missions and within the teams in the mission. There are many working groups that I encourage you to participate. Here you have all information about the working groups ongoing, talking about comets, talking about observations or a specific activity in Solar Orbiter community. And the data is available for everybody, so you can enjoy. The instruments collect the data. They have 3 months for calibration and preparation of the data. And after that, ESA first and then NASA put this data publicly available for the community. And as you see, this is Solar Orbiter. This is a beautiful animation on how Solar Orbiter is facing the sun and observing and bringing these beautiful observations and findings of the sun. So thank you very much.
Wonderful. Thank you, Doctor. Really fascinating stuff. The presentation, just beautiful images, and it's just lovely. Thank you for that. It was really good stuff in there. Franco, who had actually booked you, I think could start with the first question here. So, Franco, if you have a question, let's start with you. You got to unmute yourself, Franco.
Yeah,
there
I
you go.
did. Actually, I wanted to ask if there is like a public portal for data from the Solar Orbiter, including images that can be downloaded or processed, or
So I put it in the presentation, but I also can send you later the link.
Yes.
There is a platform. There are two platforms, one at ESA and one at Earth. Oh, sorry, and NASA. And then at ESA is in a SAC. And then also once is publicly available there, we mirror here at NASA, and then is PDF is the facility that we have at Goddard, is publicly available, the in situ data and the remote sensing data.
Thank you. So look forward to receiving your information. Thank you.
Sure.
I got a couple questions here from one of our members, Keshav Nair. So if you could explain the difference between the solar orbiter and the Parker Solar mission. So Parker Solar mission, I know a little bit about it, that they got Parker Solar, they have the fastest man-made object ever. Will the solar orbiter do the same? It's going to get closer.
So there are solar orbiter. I didn't talk about Parker, but solar orbiter and Parker are sisters. They actually, the communities overlap, and they have been working all these years during the planning of the mission. Have been working together, and we are working together with Parker mostly because they are complementary missions. Parker Solar Prof is a mission that just have 4 instruments, and the reason is because first it requires the orbit is more challenging. Parker is touching the sun surface. It's gonna get 10 solar radius of the sun. It's touching the sun surface. So the orbit is faster, requires a more accurate and precision in the orbit. In the case of a solar orbiter, is very heavy, comparing with Parker, heavy satellites. Is 10 instruments, and therefore is going to be farther from the sun. It's not going to be so as Parker. However, it's going to provide more remote sensing observations. So in the case of Parker, there is just one heliospheric imager. It's very similar. It's the same team. It's called. I talk about Solo High. In Parker is Whisper. Whisper is the same instrument on board the 2 satellites, but in the case of Parker, it's just that instrument. In the case of Solar Orbiter, we have then coronagraph, we have EUI, we have PHI, we have telescope observing the sun surface. So working together with the Earth observatories, we have a better view of the heliosphere and the sun. So there are 2 different missions, but they are complementary.
Great. He had another kind of a follow-up question here too. If you could explain the speed of the plasma solar wind as it comes off, how long does it take from the time that it comes off the sun to go a full AU till it travels to us?
Well, it depends. As I say in the very first slide, the velocity of the solar wind goes from 800 kilometers per second to 800 kilometers per second. But when we have these storms, can reach velocities of 2,000 kilometers per second. In that cases, a solar storm can reach the Earth in 24 hours. So sometimes the coronal mass ejections takes 3-4 days, but it can take just 1 day. It depends. And how can we predict this? Well, it's a challenge. We have people observing the sun all day, 24/7, and seeing, active regions. At Carrington did, but these are a little bit more professional now. And then, so we are able to track a little bit at this velocity now with more precision.
Let's go back to the Carrington event too, because that it's always been fascinating. People, it's such a doomsday event, and of course, if something like that happened now, we're in the Stone Age. It's really, it would be very difficult to recover from something like that. And that across wherever there were telegraphs, it actually set the telegraphs on fire. And I think that a lot of people here in New England remember when New York the power went out in New York. It went out here in Connecticut because of a solar storm. What was it? Maybe 20 years ago now. Was that I can't remember if it was the one that caused the stuff in Quebec or not. But what are the chances of these things happening again? Are we prepared for this? And will these types of things help us prepare?
Well, I can tell you that we are prepared. We are preparing. We are now doing the exercise. There are several reports, and there are also mandatory commands, let's say, from the White House to get prepared, to be prepared for these kind of events, because we know that the impact in the society, we are starting to do reports in terms of how will be the cost in the society in the case of having one event similar to the Carrington event. So we are right now, for instance, NOAA is preparing, is working on that, is working in doing a proper forecast. At NASA, we are working with NOAA also, but in our case, we are working to protect our technology and astronauts in the space. But we are all working together also with the international community, working to prepare our societies for these kind of events. Are we prepared? Well, it's a work in progress.
That's a good answer.
I have a little bit of a follow-up on that too. One of your earlier slides, you were showing solar cycles and how over time there's a trend towards weakening, and I'm wondering if that suggests it's less likely that we would see such an event.
No. I'm sorry to say no, because the fact that the activity of the sunspots is less, it doesn't mean that one event can be stronger. So actually, it's very interesting that sometimes stronger events are not happening around the maximum. It's actually happening in the rising or declining phase of the solar cycle.
Mm-hmm. Yeah, I guess if you have fewer sunspots and you still need to release the same amount of energy, they could get stronger for that reason.
So also, well, this is a very interesting discussion also, because when you have, let's say, you have several, as we see in 2013, several explosions, all of them became a mess. Let's say, let me use this kind of vocabulary. It became a mess in the solar wind. One of the things that trigger the geomagnetic activities is the well-organized magnetic field configuration of these structures. When we have just one single big event, means that this event is not going to be disturbed but any other. So when reach the Earth, reach with this well-organized magnetic field configuration that can trigger the reconnection with the magnetosphere. So that's also why in the rising phase or declining phase it's more probably to have these kind of big events. Mm-hmm.
Got it.
I had a question from Jan Degenschein, who said, wonderful presentation. Since we have recorded the effects of extreme solar flares in various locations on planet Earth, are there any parallel studies of these phenomena on lesser conductors like individual human beings? That's a crazy question.
So on Earth, it is affecting not the Earth, on the human beings?
Yeah, I would say that, I think that might be more of a biology question too, because obviously as the radiation goes in and out to Earth, as we get hit here, it knocks out DNA on plants and animals and critters, and that obviously does change, over history. I'm not sure if that's.
So, I know there were. I read few studies trying to relate more the solar activity or the solar cycles the human health, let's say. Still, I didn't see any good results relating the solar cycles, for instance, with the health, let's in general. We humans have been on Earth for millions of years, and the sun has been active for millions of years. Our DNA, I will say, is get used to the sun activity at the ground level. So here at Earth, if something is happening in the sun, we are protected by the magnetosphere. However, the problem happens when we go higher in the atmosphere. So when we move, now that the humans want to go in planes and go later International Space Station, and we are thinking to travel to Moon. So the problem is we are gonna go to an environment which our DNA is not get used. So that's when these studies are starting to, and NASA is focused in these kind of studies to trying to understand how the lack of gravity and how the radiation is affecting our body in general. But it goes more when we go beyond the protection of the magnetosphere. Mm-hmm.
Any other questions from the panel? I have just one last one then. So what is the future that you see? What other kinds of things can we study on the sun? And I know that there's a couple of, there's a CubeSat right now that's going up, that went up on Artemis 1. And then the Indian Space Research Organization has a launch coming up here this year to go to the sun. What are the future kinds of probes that we can expect to see coming up from NASA and ESA, and what's next?
So Punch is one of the coming missions that is going to be launched next year in 2024, and then we have also to study the sun. We have Punch is the one that we have to be focused. It's a polarimeter that is going to be 2 small satellites that are going to be observing the sun and providing new insights, mostly focusing the transients in the heliosphere. So we are preparing several, and right now we are also competing with other missions concepts. And we are thinking about, obviously, small satellites are the more now challenging, but also exciting, new perspective of exploring the space. So yes, we have a lot of new ideas, let's say, what's happening.
Great. Well, I think that's going to stick a fork in tonight. So thanks so much, Dr. Teresa. Nieves, Chinchilla, thank you very much. It's been a pleasure. Thank you. Thank you for joining us today.
Thank you for having me. It was very fun. I'm sorry for all these technical things at the beginning.
Thank you. That was a Carrington event.
Well, the good news,
probably a solar flare. There's a lot. You can see the auroras behind it.
Right.
The good news is when this is up on YouTube, you'll never see any of this, and that's a good leader too. Is that we have all of our many of our past talks up on YouTube in the archives. They're in playlists between each year, and they're fascinating to go back and watch. There's some really great old ones. We've been around for almost 48 years now, so there's some good ones that are up there that Alex has posted. And next month, we hope you join us for Dr. Regina M. Caputo. She is a NASA Research AST Fields and Particles scientist. She's going to talk about dark matters, the search for the universe's missing mass. So we hope to see you next month. And until then, thanks so much for the tuning in to the Westport Astronomical Society lecture series. We'll see you. Bye.
Thank you.
Thank you.